I start by saying a few things about the homework. Well, most of the solutions are in the back of the book, so I will not discuss much solutions, only side remarks I make. And I start with exercise 4.2.3 that you see here displayed already. This exercise, well, we saw before when I defined subjective expected utility for uncertainty with both utilities and probabilities unknown, it seemed that it will be very difficult to measure these concepts because for one you need the other, but you don't know either. You don't anymore deal with linear equalities. We saw already in the experiment, the homework we did before, that maybe it's not so difficult after all. In the experiment, we already measured using these alphas, we could already draw the graph of your utility function. And you can imagine that we can do it more refined with more detailed measurements. We can get to know the utility function and the graph very precisely. Once we have that, we can also measure the subjective probabilities like we did in chapter 1. So it is not so very difficult after all. Exercise 4.2.3 shows another way in which it can be easy sometimes. In this exercise, we have three equally likely events that partition the state space. Then you immediately know they must all have the same. Equally likely means you just much like to gamble on them, If you get €100 on each, you're indifferent between them. That's how I mean equally likely. Anyway, then from that you can easily see that they must all have probability 1/3. Then the union of two has 2/3 and so on. And then once you have those probabilities already, from the indifference here, you can already find out what the utility of 25 must be. So here's another example where sometimes things are easy. In general, although we did in the experiment with alphas getting utility quickly, there are also ways to get probability quickly. If you can partition the state space into equally likely subsets, and equally likely means again in the gambling on sense. For instance, you can split it up into partition containing thousands single events that are all equally likely. Then you immediately know they must all have probability 1/1000. Then for any union, for any j over 1000, you have an event with that probability already available. Well, once you have probabilities in that refined manner, you can already quite precisely measure utility using standard gamble techniques, because now you know many probabilities. So in general, getting equally like a partition of a state space is another easy way to measure the subjective expected utility model. But we will not discuss it, it will not occur further in this course, but that can happen. Next exercise, I want to say something about 4.2.7. Yes, that's again, we saw something similar with risk, that is the uniqueness of the utility function. Here again, you can multiply with any positive sigma, you can add any constant tau, it doesn't matter, same reasoning, so not much more difficult. Here again, I can raise a question that is not asked in the exercise, but that we also discuss with risk, and that is there more liberty, or are these the only utility function possible? And the reasoning that we use for risk to show there are no more possible cannot readily be used here, because we then use this standard gamma measurement where you have all the probabilities available. That is not the case here. Probabilities need not be available, and also they are not directly observable. So here it is more difficult, but still it turns out that also here there are no more utility functions. There is no more liberty for utility. It can be proved here also. It's a bit more difficult, but in fact, from the alphas, you could already more or less see it, because we already saw your alpha 0, alpha 4, if you measure fixed utility there, then for the other alphas, alpha 1, alpha 2, alpha 3 is uniquely determined. So there you had only 2 degrees of freedom. So that gives already a bit of a feeling indeed, and by refining such reasoning and taking limits and all these things, it can indeed be proved there is no more liberty than what we already have. So in that sense, it turns out to be the same as risk, although the proof is a bit different. Next exercise to discuss is 4.8.1. Here you show that the expected utility theory implies a sure-thing principle, and the sure-thing principle, we will not discuss so much in this course, it happens to be, but still it's a very important condition. It's the dividing line mostly between Bayesian and non-Bayesian approaches. Many people like me call themselves Bayesians. They say, we think that expected utility is a normative rational model. And then it's mostly a sure-thing principle. We say that is a rationality argument condition. many people disagree. They propose models that deviate from expected utility, and they say, we think that these models are rational, and then they are violating the sure-thing principle. So then they bring up arguments that the sure-thing principle is not a rationality condition. So it turns out that mostly the sure-thing principle is the dividing line between Bayesianism and non-Bayesianism, between what many people consider, me too, consider rational or not rational. So therefore it's an important condition. But in this course, we will not discuss it much more. Exercise 4.8.3. Here you can show that in the experiment, if utility is concave, then the alphas get more and more wider spaced apart in monetary units. Every new alpha j is a bigger increase relative to the previous one than the increases that we saw before. That implies that utility is concave. Sorry, that is implied by utility being concave, but what I just said is true. Also, this implies that utility is concave because whenever you have a non-concave utility function, you can set up an experiment with the right stimuli, measure such alphas in the right manner, that they reveal that utility is not concave. So in that sense, this is an if and only if condition, necessarily insufficient. Exercise 4.8.4. There we see again risk aversion if and only if expected value is preferred to the prospect. Same definition as we saw with risk, but here it is for uncertainty and for subjective expected utility. And then what is a drawback? I immediately give the answer. The drawback of this criterion is that the probabilities that you use to calculate expected value are not directly observable. They are not directly given. You have to infer them from the preference relation or whatever. You have to find out about them. So therefore, this is not a directly observable criterion. That makes it a bit less nice in many situations. It still holds here, and you need not prove it, but you can still see that risk aversion if and only if concave utility. But then concave utility, as I already told you, this condition of risk aversion is not directly observable. But then just a moment ago, we saw that this experiment that we did with the alphas, there's an alternative, in fact, necessary and sufficient condition for concave utility. And that, if these alphas satisfy that condition, that is observable quite directly. So indeed, that is then, in many respects, a more useful criterion for characterizing concave utility, and you can call it risk aversion, than the expected value criterion that was written here. Exercise 5.1.1, I want to turn to. There it is. Here we assume we have a particular data set, a bit of a poor data set within, with only the prospects with one non-zero outcome. And we assume we have risk aversion of a particular kind described in the exercise. And here we find that you can just as well accommodate it using expected utility with a concave utility function, the square root function, as that you use rank-dependent utility probability weighting. You take the square function for probability weighting, and you in fact assume linear utility. So in this case, concave utility and that convex probability weighting function are what they call data equivalent. They are different ways for accommodating the same data set, the same observations. There have sometimes been misunderstandings. Some people thought that rank-dependent utility probability weighting was just an alternative way of accommodating risk attitude in the same way as the utility function under expected utility does it. Well, in this particular exercise, in this particular context, it holds true, but that is only because the data set is so poor. Whenever you have a bit richer data set, a bit more complex phenomena, then the risk attitudes that you model through probability weighting are really different. They have different properties than the risk attitudes that you can model using the utility function. For instance, as we will see, with probability weighting, you can accommodate the Allais paradox, but with utility and expected utility, you cannot. And this better be the case, because if rank-dependent utility wouldn't bring any new empirical phenomena, it would just be an alternative way of describing things that we can already describe. It wouldn't be much news. It would be a bit unfortunate formula, and nobody would be interested. Of course, we have this extra complexity of developing that model and the more difficult mathematics, because we can accommodate, describe, and understand more phenomena. much of that is to come in the rest of this course.